Good afternoon and welcome back. So this is the last talk of today, and it is my pleasure to introduce Professor Eduard Feireisl from Czech Academy of Sciences. He completed his PhD in 1986 at the Czech Academy of Sciences. From 86 to 88, he was an assistant professor at the Czech Technical University, and since 1988, he has been affiliated with the Czech Academy of Sciences. And today he is going to talk about on the long-time behavior of open fluid systems.
Okay, thank you very much for this introduction. I hope you can hear me and you can see the slides. I would first like to thank the organizers for this invitation. I mean, unfortunately, I couldn't come in person. I must say I am strongly against Zoom meetings, but since organizers insisted, I will deliver a Zoom talk, although I would prefer to be there in person, but unfortunately the schedule was so tight this time that I couldn't make it to Bengaluru. However, it's not my first time in Bengaluru. I visited several times in the past. So today I will speak about the problem of the long-time behavior of open fluid systems. This is actually joint work with Lu Yong from Nanjing and Agnieszka Świerczewska-Gwiazda from Warsaw. And let me start with some short introduction. Reminding you what is the main difference between the so-called closed systems in fluid mechanics and open systems in fluid mechanics. I think closed systems, which is not the main topic of this talk, are characterized by the statement by Rudolf Clausius, which is written here in German, but I will try to translate, which means that the energy of the system is actually constant because the system is closed, so there is no way to gain energy from outside or to lose energy inside. And at the same time, the entropy, okay, he says world in German means world. However, we should imagine that the world means like a system, closed system. The entropy, on the other hand, of the system is increasing and approaches its maximum when time goes to infinity. And indeed, this statement can be proved mathematically. I will show you examples of the systems that describe the motion of compressible viscous fluids, where temperature is taken into account, where this can be really proved rigorously. So from this point of view, of course, the dynamics of closed systems is a little bit boring, since when time goes to infinity, the system actually stabilizes to kind of equilibrium solution, the motion is stopped, and the entropy reaches its maximum. So from this point of view, the dynamics is not very exciting. On the other hand, the open systems, which are usually used in the description of turbulence, are characterized by the so-called ergodic hypothesis. So the open systems in general, they are allowed to exchange the energy and also maybe mass and other things with the outer world. And then the dynamics, of course, can be much more interesting. And you really don't expect the scenario of Clausius to take place. However, there is a hypothesis, which I don't know if I should attribute it to Kolmogorov, but I just use his picture there because I think he contributed a lot to the theory of turbulence, which means that actually, if you take the time averages, well, the system, the ergodic hypothesis postulates the existence of a kind of measure which will describe the behavior of the system in the long run. So if you take in large enough time and you do time averaging with respect to the large time, then this the resulting behavior of the system should be characterized by some kind of probability measure. And this is indeed, so I will make, of course, we are very far from proving this statement for like realistic systems like the Navier-Stokes Fourier system. However, on the other hand, I can show you some partial results in this direction. So this is basically the main idea of the whole talk. So let me start by introducing the system I have in mind. This is the so-called Navier-Stokes Fourier system. Although it may look a bit complicated, it is the simplest possible system that takes into account, a system that describes a motion of a fluid, which takes into account the three basic physical principles: the mass conservation, the momentum balance, and the internal energy balance. So here the unknowns are the density of the fluid, the velocity of the fluid, the pressure, which is now, so that's the first equation describes the conservation of mass. The second one is momentum balance or Newton's second law. So there's a new quantity which is called pressure, which now it's determined constitutively. So I assume that it's an explicit function of the density and of the temperature. And on the right-hand side, you can see the divergence of a tensor, which is called viscous stress. So I will assume in my talk that all fluids are real, meaning they exhibit some viscous effects, because in the real fluids, the energy is always dissipated through viscosity. I mean, so in contrast with perfect fluid described by the so-called Euler system. And in order to keep some physical applications, I assume that the momentum equation, or that the fluid, the mechanical motion of the fluid, is driven by the force, which is basically gradient of some scalar potential. So if you think about the physical meaning of this force, it is of course gravitation. And on the other hand, I don't know about many other forces that would somehow act on the fluid and were not in this form. Of course, I'm completely neglecting the possibility that the fluid might be electrically conducting, or other phenomena, chemical reactions and other things. I only assume that the fluid is heat conducting. So the third variable is the temperature. And so we need, beside the equation for rho, for U, we also need equation for the temperature, which is the so-called internal energy balance equation, or if you want, the first law of thermodynamics, which is written on the third line. And here you can observe that the energy contain, I mean, the temperature equation contains a term which is proportional to the viscosity and is always non-negative. And this is the term that is responsible for the irreversible transfer of the mechanical energy into heat, which is somehow described by the Clausius statement. Now, to be specific, of course, the system is still not well determined, because there is still much more unknowns than, much more unknowns than equations. So I do some constitutive assumptions. I will assume that the fluid is linearly viscous, which means that the viscous stress is given by the so-called Newton's rheological law, and the heat conductivity is determined by the Fourier's law. Right? This is why the system bears the name of Fourier. And so that's my system. Still, you can see that there is the pressure here and the internal energy that are still not being determined. So we still have to prescribe some constitutive relations for this in order to get a mathematically well-posed problem. In order to do that, I remind you, or I recall some thermodynamics principles. I assume that actually the internal energy and the pressure are functions of the density and of the temperature, and as such can be differentiable. And if I compute this quantity where D just stands for the differential, the second law tells me that there is a new quantity which is called entropy, which is the property that if the expression on the right-hand side is divided by the absolute temperature theta, you get a perfect gradient or perfect differential of a new quantity, and this new quantity is called entropy. Now, writing down the equation for the entropy, you can write down using the previous three equations. You can write down an equation which is formally dependent. I mean, it can be derived from the first three equations, from the first three principles. However, as we will see, at the level of the so-called weak solutions, this equation will play a major role in the analysis. So this is the so-called entropy equation. You can observe the entropy flux. And the entropy, as you can see, is not conserved. There is a source term on the right-hand side. And if you still remember what is Q, which is the heat flux, it's minus kappa gradient of theta. So the second term is just proportional gradient of theta square. And so the whole thing, the whole expression on the right-hand side of the entropy equation is non-negative, which means indeed that in accordance with Clausius' statement, the entropy is being produced, so it's likely to attain some maximum unless some energy X exchanged with the neighborhood, with the neighboring world. Finally, I make the hypothesis of thermodynamic stability, which can be expressed in different ways. One of the most elegant ways, which is quite convenient working with weak solutions, is to say that if you write down the formula for the total energy in terms of the momentum, which is rho times U, and the total energy, total entropy, which is rho times S, then this total energy is actually a strictly convex function of these quantities. And as you know, since I will use frequently in my talk weak topologies, convex functions are weakly lower semi-continuous, so we amply use this property in mathematical analysis. And this is still not enough. I will still have to assume something more about the constitutive equations, but we will come to this later. Okay, so let me start with the conservative systems I mentioned at the beginning of my talk. These are systems where several quantities are conserved. So I assume that I have a bounded domain. I will always assume that my fluid occupies a bounded domain. Physical domain is bounded. The system can be considered in 1, 2, or 3 space dimensions. Mostly I will focus on the dimension 3, which is physically relevant. And I will assume that the velocity on the boundary is prescribed. And so in particular, if the normal, so if I prescribe 0 boundary velocity, which is done on the next line, which is typical for the so-called no-slip boundary condition, then in particular, the normal component of the velocity is 0. And integrating on the boundary and integrating the equation of continuity, you will find out that the time derivative of the this quantity is the total mass of the fluid is equal to 0, which means the mass is conserved. The total mass of the fluid stays the same, which also from the mathematics point of view, this provides some kind of a priori estimate. At least you know that now the density is bounded in the space L1 as soon as the initial data have finite mass. Well, if you prescribe also the heat flux, which is 0, which means now the fluid system is really closed. I mean, there is no flux of flux of energy through the boundary. Then you will find out that this quantity, which happens to be the total energy of the system, is also conserved, which means its time derivative is equal to 0. And now you see, since I mentioned on the previous slide, if you express this quantity as a convex function of rho, m, and s, this gives you some estimates, a priori estimates on rho, m, and s, as long as you assume the same thing for the initial data. Finally, there is also the entropy production, which now, because we have conservative boundary conditions, can be written in this form. The entropy balance can be integrated, the boundary terms disappear, and you finish with the expression that the time derivative of the entropy is equal to the quantity which is on the right-hand side, which is non-negative. So it now, according to Clausius, the total amount of entropy of the system is indeed increasing, is an increasing function of time. And since in many practical cases, the entropy can be controlled by the energy, this gives you some bound on the entropy production. And so in particular, you see that, well, you will get some bound on the gradient of u and some bound on the gradient of theta. And these are bounds that can be used in the analysis, for instance, in the very weak solutions of the system. But let me remind you, this is the conservative system, so that's a simple situation. For conservative systems, so let's specify the boundary conditions. So I take the conservative boundary conditions of this form. I take the driving force, which is the gradient of some x-dependent function, so it's like gravitation. And now, indeed, what was like predicted or what is claimed in the statement of Clausius can be made rigorous in analysis. So this is a result we proved long time ago with a colleague of mine, Antonin Novotny. You can introduce some concept of global in-time weak solutions for the conservative system, which are based on the energy balances and weak formulation of the field equations. And you can show that any weak solution of the system actually complies with Clausius' principle, which means when time goes to infinity, the density goes to some rho s, which is a function depending on x only, and the temperature goes to temperature depending on theta s. So these are time-independent profiles, and the momentum goes to 0, which means the fluid stops the motion at infinity. When the motion for large time of a conservative system is 0, the fluid is not moving, and the quantities rho s and theta s satisfy the so-called static equation. So they form the so-called static state, which, they solve the equation gradient of the pressure is equal to rho as gradient of g, which somehow follows on the momentum equation, assuming the velocity is 0. And, well, of course, this equation itself has a lot of solutions. However, if you fix the total mass, then you can find out that there is a unique solution of this problem, and there is a unique limit of the system when time goes to infinity. So this is this is what can be proved for conservative system, and that was proved more than 20 years ago. Now let's consider the open system. I will take a very simple open system. Of course, I can have more complicated examples, but I want still assume that the mass of the system, total mass of the fluid, is conserved. So I still take the no-slip boundary conditions. I assume that the velocity on the boundary is equal to 0. However, I prescribe the temperature on the boundary, which is given by some field theta b, which is not constant. Now, if you think about practical examples, the iconic example of this problem is the so-called Rayleigh-Bénard convection problem, where the fluid is confined between two parallel plates. The plates are still, they are made of impermeable materials, so there is no slip boundary conditions on them. However, they are heated. The bottom plate and upper plates are heated, and they have in general different temperature, which excites fluids to start moving. So this is a very simple example of open system. Let me show you already that there is a trivial observation that actually open system may not have. On the previous slide, I showed you that all solutions of the conservative system will tend to equilibrium, where the equilibrium is actually characterized by zero velocity. This is not the case in general for open systems. In this very, very simple example, it may happen that actually equilibrium solution with zero velocity, which is sometimes called static solution, may not even exist. So if the system is at equilibrium, meaning if the motion is time independent, then the velocity is not zero, which means that the fluid is still in motion. The only thing is that the velocity is independent of time. So how you can see that? Well, it's a very simple calculus that I provide here at the bottom of this slide. So assume that I have a stationary solution of the problem, solution which is independent of time, which has zero velocity. So I have the zero velocity, US stationary velocity is equal to 0. If this US is equal to 0 and everything is time independent, you can easily deduce from the balance of internal energy that actually the temperature, the static temperature, must solve this equation, which if you think, for instance, that kappa is constant, this is nothing other than harmonic equation. Laplacian of theta is equal to 0. However, theta s is given on the boundary. It satisfies the boundary conditions of this problem already has a unique solution. The solution is uniquely determined by the boundary conditions. Now I go to the equation of momentum, and you will find out that analogously to the previous slide, the static density and static temperature must comply with this equation, which is the equation between a gradient on the left-hand side and something that's not a gradient on the right-hand side. So actually, it should be gradient. So taking the curl of the left-hand side and taking the curl of the right-hand side, you will find out that curl of this is actually gradient of rho s vector product with gradient of g. This relation tells you that actually gradient of rho s is parallel to the direction of the gravitational force. Now you rewrite this gradient of the left-hand side in more details. You write it as a gradient of the pressure with respect to rho, then gradient of rho s, and gradient of the pressure with respect to temperature, then gradient of theta s. And now you assume that this is a non-zero quantity. Taking the vector product of this equation with gradient of g, you will see that on the right-hand side we have 0 because of the previous slide, and because gradient of g cross gradient of g is 0. On the left-hand side, gradient of rho s gradient of g will disappear because of this relation here, and you end up with the relation that gradient of theta s cross gradient of g is equal to 0, which means again that the gradient of theta s is parallel to the direction of the gravitational force. However, theta s is already given by this equation, so you can easily, find a situation when if you prescribe the theta b in some way, some specific way, theta s, the gradient of theta s will not be parallel to the gradient of the gravitational force, and which means this will never be satisfied. So such a solution with vanishing velocity does not exist. So from this very simple example, you see that, well, the behavior of open systems is really much more interesting because at least the static solution do not exist. So the stationary solution must have a non-trivial velocity. And actually, the question of stability of stationary solution with non-trivial velocity is an interesting problem. And we are far from having a complete solution to that. But at the end of my talk, I will show you some example what can be shown about stability of non-static stationary solution, meaning solution with non-zero velocity. Well, so, but let me start with the theory. So the previous slide suggests that actually in order to study the behavior of open systems, I have to deal with large solutions out of equilibrium. For closed system, we have seen that all solutions basically stabilize to equilibrium solutions, which means that if you start in a neighborhood of this equilibrium solution, you would expect your solution will stay in that neighborhood. And there are nice perturbation results that say that, well, in this case, actually the system has a smooth solution. If you have a closed system and you start in a neighborhood of stable equilibrium, you can prove the existence of global in time smooth solutions. So actually you can stay in the framework of smooth solutions. Speaking about open systems, you have to stay in this, you have to consider the weak solutions because you expect the solution to be a large deviation of equilibrium. Now, what is the main problem? The main problem starts, so in order to develop the theory of weak solutions, you need a priori estimates. As we have seen, for the closed fluid systems, there are a priori estimates which are actually can be derived from the three basic physical principles: conservation of mass, conservation of momentum, or conservation of energy, and production of entropy. For open systems, this breaks down because, well, you still, since I have no slip boundary conditions for the velocity, you can still infer that the total mass of the fluid is constant, which gives you L1 bound on the density. However, if you go to the energy equation and you write down the energy balance, you will get the time derivative of the total energy is equal to minus integral over omega q dot n. Q is the heat flux. In the conservative case, this term was zero, so we had conservation of energy. In the non-conservative case, this term is not zero. What is more, since we impose the differential boundary conditions, we have no information about how to control this term. And in addition, I said that we will be in the framework of weak solutions. In that case, this term may not even make sense, since the regularity of weak solutions is not enough in order to guarantee that there is a trace of the, because Q is just proportional to gradient of theta, and there is no guarantee that there will be a trace of the temperature gradient. So this term is not controllable. The same problem appears with the entropy balance. If you write down if you integrate the entropy balance, you will find out again there is that it is proportional to the entropy production rate, which is a good term because it's non-negative and provides estimates. However, there is another term which corresponds to the entropy flux, which is of the same nature as the previous one. So it's like Q dot n on the boundary, and it's multiplied by 1 over theta. And so these two relations separately don't give you any estimates. However, there is an elegant way out. Instead of considering the balance of entropy and energy separately, you introduce the so-called ballistic energy, which somehow combines these two quantities. So it is the energy minus the entropy multiplied by some function. This function is arbitrary. Usually we take it smooth. And the only property we require, it's like this function plays the role of some reference temperature. And the only property we require is that it satisfies the boundary conditions. Now, if you write down the balance for this quantity, it turns out that on the boundary, you will get a combination of these terms. You will get the first one, which comes from the energy, but in the entropy balance, there will be this term, but it will be multiplied by capital theta. However, capital theta and small theta on the boundary coincide, and so these two terms will cancel. So actually, for this quantity, you can write down some kind of, I will not say conservation laws, or even, this is a kind of relation which contains the time derivative of the ballistic energy. The name ballistic energy goes back to Ericsson, which is like energy minus entropy multiplied by some reference temperature, and plus the something non-negative, which is the dissipation term, is equal to the quantity on the right-hand side. This is still not the end of the story, because now at least you have some relation between the time derivative of the total energy and other quantities. However, even in this case, it's not obvious whether or not this relation will give rise to some suitable bounds. You would like to use this relation in order to say that the energy or entropy, or ideally both, including the production rate, are bounded, similarly to the conservative case. However, now there is a right-hand side, so of course the natural idea is to use some kind of ground wall argument to control. So for that you have to control the right-hand side by something on the left-hand side, like by the energy or the production of entropy, or both. It turns out that this can be done. However, in order to do that, you need some special assumptions concerning the constitutive equations. In particular, for the standard choice of constitutive equations, which is we will see it on the next slide, which is Boyle-Mariotte law plus the related entropy. This relation does not give you, at least I don't know how to derive from this relation, any a priori estimate. So if I exaggerate, even at the level of a priori bounds, it's like impossible to think about some existence of weak solutions without assuming some extra conditions or some more conditions, I would say physically relevant conditions, on the entropy and internal energy. And this is indeed the case, what I explain on the next slide. So I will show you something about the constitutive theory for the problem. Let me remind you, I still assume that well, my pressure, entropy, and internal energy satisfy the Gibbs law. Now, in addition, I said I assume the hypothesis of thermodynamic stability. I wrote down on the second slide, I think, this hypothesis in terms of the total energy. However, it can also be expressed in terms of the pressure and internal energy if you write them down as functions of rho and theta, as functions of density and temperature. In particular, thermodynamic stability is equivalent to saying that the pressure is an increasing function of the density, which physically means that the compressibility of the fluid is positive. So the more you squeeze it, the more resistance you feel. And the second condition tells you that this is derivative of internal energy with respect to theta. I mean, the interpretation of this term is specific heat at constant volume, and we also assume that it's positive. So these are quite natural assumptions. And now I will go back, I will go to the pressure equation of state, and I will use these two principles to derive some reasonable equation of state. In the equation of state there is always a quantity which is called radiation pressure. It's at the level of pressure, it's represented by the term which depends only on the temperature. And going back to Gibbs law, you will find out that in the equations for the internal energy and also for the entropy, I always have term which corresponds to this radiation pressure and radiation energy, radiation entropy. Actually, this term has a physical interpretation. However, strictly speaking, it is there because of mathematical reasons here, because it somehow restores compactness on the temperature on hypothetical regions where the density vanishes, which goes back to the existence theory. I really do not want to go into details how the existence theory can be developed. However, this term is needed for the existence theory, but it's also physically relevant. What is more interesting is this term, which corresponds to the standard part of the pressure. So I will show you that basically I can assume everything what you would assume for the so-called Boyle-Mariotte equation of state, except the last assumption, which will be on the next slide. So first, I assume that my material is a monoatomic gas, which means that the pressure is related to the internal energy and density by this relation. So the pressure should be 2/3 of rho times E. Now, the corresponding internal energy, of course, is given by this formula. If you apply Gibbs' law, then you will find out that the pressure Pn actually must be of this form, which looks a little bit mysterious because there is a temperature to some power times some function P, which is arbitrary for the time being, of the quotient rho over theta 3 over 2. The simplest example of the function P is, of course, the linear function. If P is a linear function, you will see that this gives rise to the standard Boyle-Mariotte law, rho times theta. The pressure is rho times theta. However, P must satisfy also some other conditions. In particular, it follows from the thermodynamic stability hypothesis that P prime of Z must be positive, and we also need this condition, which corresponds to the specific heat being positive function of increasing function of temperature. And we also assume this. Well, actually, it does not follow from this. We assume this extra condition that actually this P function behaves, it dominates from above. It behaves like a linear function. At least it's bounded. P, it's bigger than P bar by Z. So, which means up to this moment, I can include the standard Boyle-Mariotte equation of state, which is like very good. Now I write down the form of the entropy, which is necessary in this form, where S is some function. We know that for Boyle-Mariotte law, S is a log function. And now the last condition I impose, which is not satisfied by standard Boyle-Mariotte law, but which helps you in this context to find a priori estimates, is the so-called third law of thermodynamics, which tells you, well, that the entropy is actually vanishing when the temperature goes to 0. We know that's not true for the standard entropy corresponding to Boyle-Mariotte law, where actually the entropy goes to minus infinity because it's proportional to log theta. However, I assume this as an extra hypothesis, which is reflected by the fact that this function S must actually go to 0 when Z goes to infinity. As an argument, when this argument goes to infinity, the function S must go to 0. And assuming that, I will get from the ballistic energy inequality that I showed you on the previous slide some a priori estimate. So actually, I have to assume some other conditions on the transport coefficient. In particular, I assume that then the viscosity coefficient and the heat conductivity coefficients are functions of the temperature and satisfying certain Groves conditions. And assuming that, we develop some theory of weak solutions for the problem, because now under these constitutive equations, you can find unsuitable a priori bounds. And so we developed the concept of weak solutions quite recently for actually my PhD student who comes from Bangalore, and Nicholas Chaudhuri now is in Europe, but formerly he was a student in your institute. And we proved that, well, under these conditions, the Navier-Stokes Fourier system admits global in time solutions. So this is what weak solutions, of course, in certain sense, which is what you need. So you need existence of global in time weak solutions. What is more, of course, these weak solutions are not unique, but they still, well, at least they are not known to be unique, but they still satisfy some kind of natural compatibility principles. The first one says that if they happen to be smooth, which means if my weak solution is smooth, then it must be a strong solution. This is called compatibility principle. And then something which some people consider to be the same, but however it is not the same, is the property that if there is a strong solution of the problem, then our weak solution must coincide, which corresponding to the same data, meaning initial and boundary data, then the weak and strong solution must coincide. So these are the reasonable properties, and we have a concept of weak solutions which is globally defined in time, and so this is some object to start with. Now, so we would like to say something about long-time behavior for the problem. However, the main problem working with weak solutions is the problem of uniqueness. We know that we have existence, but we don't know if the weak solution is uniquely determined by the initial and boundary data. So, and there is a way out. Still, we would like to speak about the long-time behavior and about to speak about attractors. And there is a way out of this problem, which was, so we would like to use the language of the dynamical system theory, but we don't have really a dynamical system in the standard sense. However, George Sell some time ago proposed a very nice idea of working on the space of trajectories. Actually, we will see later on that the long-time dynamics is characterized by the behavior of the so-called entire trajectories, which are trajectories, which are solutions of the Navier-Stokes Fourier system, which are defined for any time. They are actually don't solve any initial value problem, but they are solutions which are defined for time going from minus infinity to plus infinity, and they have bounded energy. Later on, we will see that these solutions exist, and in a way, they describe the asymptotic behavior of the system. What is the advantage of working with trajectories is that now the time shift, which corresponds to considering the solution at later time, is an operation which is uniquely determined. If you have a global trajectory or even local trajectory starting from some point, you can determine its time shift. And so you can define a shift semi-group using the time shift on global trajectories, and you can use the language of dynamical systems in order to describe the long-time behavior of the problem. However, in order to do that, you need three basic properties to be satisfied, which I will show you that indeed they hold in the context of Navier-Stokes Fourier system. First, we need existence of global in-time solutions, some. This is what I, sorry, this is what I showed you on the previous slide. Actually, we can show global existence of weak solutions. The second principle we know we need is a kind of dissipativity property, which means that no matter from which initial data you start, the solution finally will enter some fixed bounded set. This is the so-called dissipativity in the sense of Levinson, and in the terminology of dynamical system, this is sometimes called the existence of a bounded absorbing set, which means that the dynamics of the whole system after some time will finally reduce to a bounded set. Finally, since you would like to show some qualitative properties, being already on this bounded absorbing set, you need compactness in suitable spaces, and this is the last property you have to show, which is compactness of the global trajectories in suitable topologies. And actually, all these three properties can be shown, and so this is the material on the next two slides. And having this, you can basically use the language of the dynamical systems in order to get other results, which are more or less a direct consequence of these. Okay, so let me start with the Levinson dissipativity or the existence of a bounded absorbing set. This is the first result we proved with Agnieszka Świerczewska-Gwiazda from Warsaw. So we consider a solution. We actually don't care so much what are the initial data. Of course, we know that the total mass of the fluid is invariant, which means that we have to deal with solution with this with a bounded mass or with a given mass. Otherwise, you cannot expect to get a unique absorbing set for all solutions because the mass is conserved. So solutions with big mass will keep big mass. So you have to assume a priori that your mass is bounded or is given by some constant n. Now, the statement is that you have, for any global solution, you can find a constant, universal constant infinity. This constant is independent of the initial state of the system, which means it is independent of the initial data. Of course, depends on the boundary data. And the system has the property that the total energy of the system, which is this quantity integrated over omega, when time goes to infinity, is bounded by this universal constant in infinity, which means that there is a universal ball, like absorbing ball of finite energy, where this energy is independent of the initial state of the system, such that all energies, whatever trajectory you choose, will finish in this bounded ball. That's the existence of a bounded absorbing set. Of course, the time, so the solution, if you want, will enter some kind of bounded set in terms of energy. Of course, this time can be pretty long depending what is the initial state of your system, because if the initial energy is very, very big, then of course the time can be very, very long. Ideally, you would expect to get some kind of decay rate for how fast the solution approaches the bounded absorbing set. Here we cannot prove such a thing. However, we can prove something which means that there is a uniform bound. We can show that while the solution starts at the time t, we can show that if the energy is bounded at this time t by some constant E0, then actually the convergence is uniform in E0, which means that for each epsilon, you can find time such that when t is bigger than this time, the solution is already and this time depends only on the initial energy and on this epsilon, such that the energy after this time is less or equal than an E infinity, which is this bound plus epsilon. So this is the first result. Some people think that this is a direct consequence of the energy inequality, or of the ballistic energy inequality. Actually, this is true. However, the consequence is not direct. And the strange thing, or the nice thing on the complete system, is that this result holds for the constitutive equations, where that in the barotropic case, if you forget the temperature and you consider only the barotropic case, you will not get the same result. So the temperature really has a stabilizing effect on the fluid motion, although the fluid is open, although the fluid system is open. So this is the first result. Now I promised the second result, which is asymptotic compactness. Here it is stated in a general way. So again, I assume that I have a sequence of trajectories. Now they are defined on a sequence of times which goes to minus infinity. This is not a typo. So I have solutions that are defined on Tn plus infinity, but this Tn goes to minus infinity. So these solutions, if you want, they approach solutions that are globally defined for any time. And I assume that all these solutions are bounded by some constant. Then I can find a subsequence not relabeled such that actually the solution converges in these topologies, which are like trajectory. I mean, topologies of functions that depend on time on some compact set, minus kk, where k is an arbitrary number, and the convergence is strong. And you can show that this limit function is actually it's a solution of the original system. So it's another weak solution of the original Navier-Stokes Fourier system. However, this solution is the entire weak solution, which means it is defined for any time on R, and satisfies this energy bound, which is dictated by the bounded by the constant from the previous theorem on the existence of a bounded absorbing set. This result, the difficult part of this statement is the strong convergence. Observe that we also have the strong convergence of the density. The density converges strongly, uniformly in time with values in the space L1. In particular, all nonlinear terms, depending on the density, are like pre-compact, and you can pass to the limit. That's not obvious for the Navier-Stokes Fourier system, because the density equation does not contain any dissipation term, so we'll not get any compactness of the density with respect to the space variable. So, for instance, the existence theory is based on proving compactness of the density using some sophisticated methods that were developed by Pierre Lyons in his pioneering work, which are based on propagation of density oscillations. Let me point out that here, this is not really of use because the initial state here is not known. So you do not control any oscillations of the density at some initial time that are necessary in order to prove compactness a la Lyons. So you have to do something more. There is a non-trivial piece of information hidden in this. And again, since my time is, well, maybe I can spend, since I have 1 hour, I can spend some time on explaining how this can be proved. Okay, So I assume that I have this density sequence which satisfies the equation of continuity. So the density is defined on Tn infinity, Tn plus infinity when Tn goes to minus infinity. And my goal is to show that actually we have strong convergence. How would you do it? Well, at the beginning, so if you look at the equation of continuity written in this form, clearly, if you start with the density which oscillates, for instance, density behaves like 1 plus sinus an x, then this equation, the equation of continuity, tells you that these oscillations will propagate in time, so you will not get compactness. However, there is a strange kind of propagation of compactness, which is the cornerstone of the existence theory developed by Lyons, which is based on some information how compactness propagates in the density field. To this end, you write down the equation of you rewrite the equation of continuity in the form of renormalized equation, which is this one. And now passing to the weak limit, you will find out that, well, if you plug in your solution at the time n and pass to the weak limit, this b is a nonlinear function. So the nonlinear function, which is some weak limit, which I denote by b bar. And finally, you end up with this equation for the defect, for the difference between b bar and b, which is in the case that you can take this p to be a convex function, this is basically a kind of oscillation defect, because for convex functions, the weak limit of a composition is always bigger than compositional with the weak limit. And if this term is 0, you can conclude that actually you have strong convergence. So this is how the existence theory is built up. Now you see that on the right-hand side, actually, you see the term which looks like this, which means that it's something you don't have under control. However, thanks to the idea of Lyons on the effective viscous flux, is something you can control. But still, in order to conclude that this quantity is 0, you have to assume that actually initially this quantity is to 0, which means that initially your solutions converge strongly. This is not the case for solutions which arise in my theorem. So if you define solutions by this shift, you will end up with an equation for this. So you take the function b, which has a special form, which is rho-Lacroix, and you will end up with the equation for rho-Lacroix, which is of this form. So you will see that there is a time derivative of d, which is this quantity plus this, which is weak limit of rho times divergence of u minus rho divergence of u. I mean, I simplify a little bit here the proof. I assume that I have enough integrability of rho in order to make sense. I mean, in order for this term to be integrable. However, the main idea is like that. So you get this equation here, but you have no information about D. D is this oscillation defect, but you have no information about the behavior of this oscillation defect at some time. But you know that this equation is satisfied at any time t going from minus infinity to plus infinity, and the oscillation defect is a bounded function. What you have to prove is that actually you can use the Lyons identity, which is really a deep observation, which means that this quantity, which a priori doesn't have any sign, can be actually expressed in this form. So it depends on the pressure. Now it is written on the in the barotropic situation when there is no temperature. However, you can do the same with the temperature because temperature is compact. So this term, in a way, is non-negative. Which means that this quantity is non-increasing. Now, what you can also show that this term here actually provides a damping which can be expressed in terms of D, which is the non-trivial of the proof. You can actually show that the D satisfies this kind of differential inequality, where this function psi is a function which vanishes at 0, and as the property is positive, that psi of z times z is strictly positive when z is not equal to 0. And since D is globally bounded and solves this inequality, it's easy to show that such D must be 0, which means there is no oscillation defect and the convergence must be strong. So that's really a kind of non-trivial ingredient of the compactness proof. Okay, now we have two main ingredients at hand, and so we can we have compactness and we have asymptotic asymptotic boundedness or the existence of bounded absorbing set. And we can apply then more or less now the result that follow a kind of, I would say it's direct, more or less direct application of the dynamical system theory, of result from the dynamical system theory. If you keep in mind that my dynamical system now is not defined like a solution at the time t, but as a time shift on the space of entire solutions. The first result which can be proved is that actually the space of entire solutions, which I denote by A, which are solutions which are defined for time going to minus infinity to plus infinity and bounded by E infinity, is a non-empty set. It is compact, it is shift invariant, which means if you shift this solution by time, by positive time, you get another object being living in this, and you can show that this is not a attractor, which is basically direct consequence of the previous theorem on compactness, which means that all global trajectories, all solution trajectories will approach in the topologies I mentioned on the previous slide, this global attractor. See, we have a global attractor. Sometimes such an attractor is called trajectory attractor, and now you can study the dynamics only on this set, on the attractor, because roughly speaking, all global solutions live on this attractor. Another application is the existence of stationary statistical solutions, which is again result with Agnieszka Świerczewska, which is again direct consequence of the existence of global attractor and compactness of trajectories. You can prove this using the standard Krylov-Bogoliubov theory. So you assume that you have a subset of this attractor which is shift invariant. Now it is convenient to work in what is called conservative variables, which is the density, the momentum, and the total entropy. The reason being that rho and m are weakly continuous. Rho is actually strongly continuous function in time. M is weakly continuous function in time. And S is not really, S is the total entropy, is not really continuous in time, weakly, but it's like Carlac function. It has limits. Okay, it's a function which has limits from the left and from the right. And you can redefine it as Carlac or Carglac, whatever you prefer. In this case, you pick up a shift invariant subset of the attractor, which can be, such a set exists, you can take the attractor, the whole attractor itself. Now, the statement is that there exists what people call stationary statistical solution, which is supported by this set. Actually, statistical solution of the problem is not solution, but it's a measure which sits on the solution set. So it's a Borel probability measure, which is sitting on on Borel sets of trajectories belonging to the closure of U. So it's supported by the closure of U. It's a compact invariant set, time invariant set. U is a compact invariant set, and the measure itself, it's invariant measure, which means that if you take a Borel set and perform a time shift of the Borel set in the space of trajectories, the measure is the same. So the measure is shift invariant. So such a solution is called a stationary statistical solution of the problem, and we can show they really exist. And you can also show that actually any omega limit set of any trajectory has the property of being shift invariant, and so it supports a stationary statistical solution. Okay, so that's the second result. Next result is somehow goes in the spirit of the ergodic hypothesis, which was announced on the very, very first slide. However, we are still very far from being able to prove a complete version, which means the ergodic hypothesis, satisfied by any trajectory. So we can only show something which is kind of, again, application of Birhoff-Khinchin ergodic theorem applied on the stationary measure or for the invariant measure. So you assume that you take you have again your stationary statistical solution, which is the measure nu sitting on globally defined trajectories, and you take a Borel measurable functions, and you assume that you have you have a solution set which is you have a solution which satisfies, which has the property. You have a stationary statistical solution which is the property that if you evaluate it at the time 0 and take the integral or the expected value, if you want, with respect to the stationary statistical measure, then this expectation, I mean this mean is finite. Then the claim is that if you take any initial data or any trajectory, almost surely in the space L1, then the ergodic average 1 over integral from 0 to t, again, this should be understood in the space, this object should be understood in the space of trajectories. If you take the ergodic average, and so which means this integral normalized by the length of this time interval, then this integral indeed converges to so there exists a measurable function f, such that this integral converges to a measurable function f, and this takes place for almost surely with respect to the stationary measure nu. So it's actually the proof is a direct application of Berhoff-Khinchin ergodic theorem, but it's a kind of first result concerning the existence of the limit of ergodic means for the complete open fluid system. Well, the last result, since I'm still left with 5 minutes, consider something what I also promised at the beginning of my talk, which is stability of stationary state. Now we know that for a general open system, the stationary state may be non-trivial in the sense that the velocity corresponding to stationary state may be non-zero. We cannot prove like global stability of stationary state, of course, because somehow it is anticipated that there are multiple stationary states, so there is no chance to prove that they are globally stable. However, we could prove global stability of small perturbations of stationary state of static stationary state. For the problem with given temperature on the boundary, you can consider the situation when the temperature on the boundary is constant. In that case, you can show that again the problem admits a trivial solution, which is constant temperature, density, which is also constant, and the velocity which goes to 0. Which is equal to 0, and that's a static solution of the problem. If you perturb a little bit, in this sense, so if you perturb a little bit the force on the right-hand side, you perturb a little bit the boundary temperature, you end up with a small perturbation of the stationary solution, which I denote rho as theta s and us. The perturbation is small in the sense that the velocity is small, the distance of the theta s from the constant temperature is small, and also the distance of the density from the constant density is small. But such solution exists, and they are locally stable. They can be shown locally stable in the class of smooth solutions, which was proved in a paper from '86 by Alberto Valli and Wojciech Zajączkowski. Sorry, there's a typo. It's Wojciech. It's not N. It's W. They can show that indeed the small perturbations are locally stable in the class of small solutions, which means that if you take a small perturbation of them, you have a global in time smooth solution. The smooth solution will converge. We could prove with young glue, and this is the last result I would like to show you in my talk, is that actually the same static states are globally stable, which means that you take the same static state and you take now any weak solution of the problem, any meaning starting from arbitrary large initial data, we can still show that these solutions are stable, which means that the solution converges, any global solution converges to the static state, no matter how big the initial data are. So this is global stability result. Again, the most difficult part of this result is the proof that actually the density converges to its limit counterpart. Okay, so in a way you can also use this framework of weak solution in order to show some global stability properties for open smooth system. And that could be one of the advantages of working in this more general class. Okay, so I think now my time is up, and so I will stop sharing, I hope. And I thank you very much for your attention.
So are there any questions? So I have a question. So in
Yes.
the global stability result, do you have any decay rate?
No, no, because the problem is for the weak solutions, it is really delicate to get any decay rate because you know, the density. I mean, again, the main point is the density decay, because I can imagine that you can prove some kind of decay for the temperature and for the maybe for the velocity, because you have dissipation. The density, you cannot even exclude. I mean, the convergence is in the LP space, right? In L1 in particular for the density. And well, you can improve it. It's actually in L gamma, where gamma is bigger than it's less or equal than 5/3. However, the problem is that you cannot even exclude that the density will develop some kind of vacuum state, which means it will approach at least on some part of the domain 0. We even don't know if the density converges kind of uniformly in this L gamma norm. This would be already uniformly in some norm which would exclude, for instance, the asymptotic presence of vacuum states. So no, I mean, of course, these results, if you go to the 1D case, you can show certain stability and certain decay rate. I mean, you can show decay rate. But in the multi-D case, I mean, the problem is, I don't know.
Okay. Another question is, what happens in a moving domain?
Sorry?
What happens in a moving domain?
Oh, in a moving domain. Well, what you want to move? You want to move the boundary like in a controllable way, or you want to have a...
Yeah, boundary of the moving with some velocity.
Yes, I don't know. We haven't studied this problem yet. I would say possibly something can be done. I would say in particular some stability results. Maybe, yeah, I mean, it's not excluded. Everything will work. For the time being, we even don't have any kind of like a mathematical theory written down for the moving domain.
Okay.
We even don't know, we even don't have the concept of weak solution, right? I mean, of course it can be done. I believe it can be done, but so far, to the best of my knowledge, nobody bothered to write it down. So we even don't have the basic starting point.
Okay, thank you. So are there any more questions? Okay. If not, let's thanks Eduard again.
I thank you very much for this opportunity.